Hello, everyone. I'm here to talk about AI, not a very interesting topic to talk about in system circles, or rather, not a very liked topic for some reason. I don't know why. But there's a lot that's happening in this space. My new venture is an AI company as well. And I believe that it's something that will have a profound impact on how we build things. And what my own personal experience has been is that the way we build AI systems is in a lot of ways completely different mental models than how we have built traditional systems. There's a lot of best practices that don't carry over as easily to AI systems, and that's what a lot of this talk is about. So I thought I'll start with this video.
Do you read me, Hal? Do you read me, Hal? Hello, Hal, do you read me? Hello, Hal, do you read me? Do you read me, Hal?
Affirmative, Dave. I read you.
Open the pod bay doors, Hal.
I'm sorry, Dave. I'm afraid I can't do that.
What's the problem?
I think you know what the problem is just as well as I do.
What are you talking about, Hal?
This mission is too important for me to allow you to jeopardize it.
I don't know what you're talking about, Hal.
I know that you and Frank were planning to disconnect me, and I'm afraid that's something I cannot allow to happen.
So this is a clipping from a very old and very famous movie. Leaving all the dystopian side of things aside, to me, this is an example of systems failure, isn't it? A system not working in the boundaries that it was defined to function in. And if we are not very thoughtful about how we build future systems, maybe not as bad as this, but we will face issues. So yeah, that's what I'm hoping to discuss with you. So to be able to talk about in what ways an AI system is fundamentally different from system, we need to characterize systems. Almost all the books define a system as a set of interconnected components which behave as a group. Behaving as a group in the sense that the group is its own distinct entity with behaviors that's a composition of all of these individual connected parts. And this overall system interacts with its environment. It has an input side of things. It has an output side of things with which it communicates to the rest of the environment. There are natural systems which have emergent behavior. For example, weather systems. These would be a function of the amount of sunlight reaching, the latitude and longitude of the place. The environment for a local region's weather would be, the interaction with weather systems with neighboring regions. Similarly, we have human-engineered systems which have designed behavior. So these are very different kind of systems, even though both of them are referred to as systems. For this talk, I'll be talking only about the human-engineered one because I am interested in the design piece of it. What's interesting is AI fundamentally has emergent behavior properties, so it really doesn't fall very neatly into either side. We would want it to have designed behavior, but the behavior itself is emergent, and that's what makes it very tricky, and that's what the recurring theme in this talk is going to be. So going further deeper into the characterization of this system, we've developed a lot of great practices through decades of human engineering. We've developed abstractions that reflect a certain amount of modularity, a certain amount of composability, and that has allowed us to build extremely complex systems. We've used these abstractions to create different layers, which allow us well-defined plane of reasoning because we've limited stack in our head. All of these abstractions that we've created is designed so that we can reason about the behavior of systems in a way that is, tenable inside our head. These kinds of concepts, like modularity and composability, can be defined in various terms, but there's a particular theme that I'm going to pick here. Each one of these concepts can be used, can be thought of as trying to eliminate a particular kind of fault. Okay? For example, when we think about modularity, we can think about that as isolating the behavior in a well-defined unit so that any time that there is misbehavior that happens, it's in some ways firewall to that unit. So that's one way we can think about modularity. Similarly, when we think about composability, we can think about it as designing systems so that the way the composed behavior of a system shows up is always in predictable bounds. It is never unpredictable. So we've developed these practices to reduce fault models. And the reason why I'm describing it in these terms is because AI's fault models are fundamentally different. That's what we'll get to in a bit. So for the purpose of this talk, I'll be defining system design as the science of characterizing fault models and the art of rendering them inert via engineering. With that in mind, let's try to characterize an AI system. I'm assuming most of us here have used some kind of AI system. Would that be true? How many of you have used AI system? OK, most of us. How many of you have built AI systems? OK, it's actually larger than what I thought. That's fantastic. So by AI, what I'm talking about here is specifically the modern generative AI side of things. So this, we've had the classical machine learning side of things of the past. I am specifically talking about the generative AI side of things. So we'll develop a high-level sense, because not a lot of people have actually built AI systems here. We'll just develop a high-level sense of things. This is a system. There's an input, there's an output, and we can describe that system as a function. What AI systems effectively do is that the function is a learned function. And we do that by throwing a humongous amount of data onto that network. And through that, it can approximate any kind of function, so long as that function meets a certain set of requirements. This is called the universal approximation theorem. And it says that a sufficiently large enough neural network can learn any function. This is the basis behind pretty much all the deep neural network things that we see. So with this in mind, there's a question. All the literature that we have, we can model all the English literature, let's say, as a sequence of tokens. And we can model that whole problem that LLMs usually address as, given a sequence of input tokens, what the output token should be, output word should be. So here's an LLM. And let's say the set of words that, in the sequence that it sees is systems distributed. It might actually predict the next word as 2024. And I put this back in as input. The output is was. So at each step, all that this is doing, this is a simple system. It has an input, which is a sequence of words, and the output is a single word. Okay? And this will keep on, So through this simple primitive, we've been able to generate a coherent sentence. This is called an autoregressive LLM. Okay? LLM is large language model. Autoregressive just means that the next token is actually going to be a function of the previous tokens that it has seen. What researchers realized is that when we build an autoregressive LLM, purely by this effort to try to predict the next token, it ends up developing an internal world model of sorts. And that becomes very handy. But the core primitive remains the same thing, that ultimately it's a function that has modeled extremely well, given an input series of words, what the next word should be. Okay? So everything else is an emergent phenomena from this basic concept. Okay? So let's say a user is using an LLM. If you notice here, the core LLM itself is just a function which maps an input series of words to a single output word. But that's not how we talk. We talk in large coherent sentences. So the way that a lot of these LLMs end up getting sort of productized is that the user doesn't interact with the LLM directly. They go via an orchestrator. What the orchestrator does is it actually keeps on feeding the generated output back into the LLM to get the next output until they encounter a token, an end of sequence kind of a token. So when there is an input from the user, what such an orchestrator does is they would actually try to put some context, some additional kind of instructions. It can be like you are XYZ created by ABC. If the user asks you to do this, then do that. There can be a bunch of instructions that can be enumerated. And this is what is usually called a system prompt. This system prompt is created by the company or the individual that created that orchestrator. So the user's input is sort of appended to that system prompt and is actually fed into the LLM, and then the output is created. So this kind of an activity is continues until you get like a coherent output. If you observe this kind of an architecture, there are two sources of knowledge that we can see. One is the kind of training that would have gone into the LLM. Second is the context window. This series of tokens, this series of inputs is called a context window. Notice that the output of LLM also goes into the same context window. So it's like a continuous stream of words that has been created. And these are the only two places that can be used to modulate the behavior of LLM as a system. The trained one and the runtime data that is actually being fed into it. It's going to be important for further slides, so just bear this at the back of mind that these are the only two places where we can modulate the behavior. Okay, so the way a lot of these LLMs are created is that we crawl everything from the web and just keep pumping that data into that neural network, okay? Because the data that we have crawled is actually a series of words. So you can model the training process as word 1, word 2, word 3, feed that, and if the word 4 has been predicted correctly, that's great. If it is not predicted correctly, then there is backpropagation or failure and adjustment of weights. So in a lot of ways, you can imagine this as a self-supervised process, and which is what has allowed these LLMs to gobble up so much knowledge about the world so quickly. Okay, so this is called a pre-training. It's actually the training process of an LLM. But the reason why it's called pre-training is the fact that once you've trained the LLMs on data like this, they're not as coherent as you would want them to be. It's like a simple web page that you would come across. That's the kind of nature of interaction that you would have with an LLM like this. So what we do is we normally end up doing a process called supervised training. This is where you would get into some level of, okay, if I pose this kind of a question to you, this is the kind of response I expect. So this is a stage where you often put in some kind of domain level knowledge as well. Let's say you are building a medical-oriented LLM or a legal-oriented LLM. This is where you would usually be fine-tuning the information. So this is, again, training in the sense that you're changing the weights inside the network, but it's oriented towards adding knowledge to the LLM. Then you would often end up doing some kind of preference optimization. This is different than sort of adding knowledge. This is usually about comparing two kinds of responses. This is where the personality of an LLM is usually developed, where you throw multiple responses, and you are training the LLM on picking which one of these two responses is more preferred. So you can sort of have a different kind of personalities developed for the LLM. Okay, these two steps are called post-training. So the reason why I was describing this is these are the only places where you can change the weights of an LLM. Remember, there are only two sources of knowledge, either the weights or the context window. Whenever we are talking about the weights, we have to touch one of these three things. Okay? So coming back to what I mentioned earlier, the fault models of AI are completely different, and the rest of the talk is going to be all about that. We'll talk about fault models that stem fundamentally from the non-determinism aspect of LLMs. We'll talk about fault models that stem from the architecture of LLMs, and those that stem from emergent behavior. And once we talk about it, I'm hoping you would get to share this idea about why our traditional system design principles don't carry over as effectively onto AI system side of things. So let's start with non-determinism. This is the first point of tension. Historically, we've treated non-determinism in a very suppressive kind of a way, right? So people here would be familiar with ECC RAM, right? Or let's say checksumming on the network packets. Pretty much any kind of communication medium, communication or storage is communication over time. We have checksumming, right? So we do that because we anticipate some kind of corruption, some kind of unanticipated modification. That kind of, it changes the deterministic behavior, so we tend to suppress it. We introduce these mechanisms, these techniques to suppress that behavior. We've also done a lot of classical ML, where we've built classifiers. So one of the questions that people often discuss is how is non-determinism different than probabilistic systems? Are they different? Are they same? Classic ML systems deal with probability all the time. These are systems that have been running for many decades now. So what is different about the new kind of these AI systems that we are building? Fundamentally, we talk about the new generative AI as non-deterministic because the output is open-ended. It is unbounded. Classical ML, we have probabilistic distribution. We sample, we train, we do all of those things, but the model itself is deterministic at inference time. So for exactly the same input, it would actually produce the same output. Modern generative AI is not like that. Okay? So it has open-ended output because it's fundamentally created for what's possible, not necessarily about what's correct. Okay? And the way this is implemented is by the idea of sampling. So on the output side of the layers, we actually sample from a distribution. Fundamentally, they are designed in a way that will lead to hallucination. Okay? It is not a bug. It's a feature. Okay? And the trouble is when these models hallucinate in a way that violates the correctness as it exists in our minds. That's when it bothers us. Otherwise, the creative part, actually, we quite enjoy it. It's only when it starts deviating from the correctness. So it's not variety that is the issue. It is the correctness that is the issue. And that is what actually makes these systems different from all the traditional systems that we've built in now. Okay? So yeah, with correctness in mind, we've got to think about how do we harness the power of these systems, these modern generative AI systems, without compromising on correctness. And that is a very, very hard problem. One of the easiest steps to do is what is known as response verification. So inside this orchestrator, we can have something like a verifier built into it. So long as the nature of output is verifiable, the verifier can work. Examples of it, code, source code, right? So we use LLMs to generate source code. Enough people do that. And what happens is we already have a great verifier of source code, the compiler. Had the idea of compiler not been there, I strongly doubt that LLMs would have been as effective in code generation. Okay? What happens is that because compilers produce great pinpointed issue, that issue of compilability is fed back into the LLM, and ultimately there's a convergence of sorts that gets done. Okay? If all that the compilers would have produced is, let's say, compilation failed, LLMs have no input. There is no new information in their context window that allows them to correct their behavior in some form. Okay? So in any AI system where we are relying on response verification to reduce hallucinations, verifiability becomes an extremely important criteria. And what that means for system designers in the AI world is to figure out how to frame the problem in a way that allows for some kind of formal verification to be done. And there's one area where I'm expecting a lot of really good work, a lot of really good research to be getting executed. So yeah, the better the verifier, that much better, that much lesser the hallucination is going to be. So response verification was one way to ensure correctness, but that's not the only way. Because response verification, remember, will just feed back the error into the context window of the LLM, and it allows the LLM to function effectively. We could also change the weights. We could have better training. The only issue with better training is that for every incremental progress that needs to be made on the reduction of hallucination, the cost actually keeps on going up disproportionately more. Okay, so let's say hallucination rate is, let's say 3%. To get it to 2%, you would probably need actually 10x more cost, and not like a incrementally more cost. Okay, so that's one issue with better training. That said, for domains, sort of one area where better training is very helpful is that if you're using an open source LLM and trying to fine tune it out to your specific domain, then obviously there's a certain level of correctness that you can get to simply by better training. Yet another would be better prompts, because only two sources of knowledge, either the weights or the prompts. Prompt engineering became a hot topic because of this reality that simply by better prompts, you can actually get the LLMs to behave. Now, there is a problem, because ideally, a system that is very sensitive to the kind of prompts is a very fragile system, if you think about it. Because a tiny change in the model or the prompt might actually, it's like one of those things where a simple change in the code breaks everything, and you're like, what happened? Those kinds of code, we typically call them as fragile or very sensitive code, and that's not a good thing, that's not a good system. Similarly is the case here, and a lot of AI systems are like this, but it's important for me to call out that better prompts definitely help you become better at AI engineering, okay? So that was about fault models that actually stem from the non-determinism side of things. Let's come to the fault models that emerge because of architecture. Fundamentally, we've got an LLM as a large function machine that converts a sequence of tokens into a single output token. We've got the context window where we have the user prompts, etc., and system prompt essentially being captured. Okay? We can imagine the LLM as the CPU in some form. Is it not? Because it's executing something to produce the output. So we can imagine this is where the brain effectively is, right? And we can imagine the system prompt as the memory, because this is the only input that is fed into an LLM. And LLM by itself is inert. It's only when a context window is sort of pushed through it, does it actually produce something. Okay, so we can think about the context window as memory in which you keep on adding more information or more Q&A between the model and the user. Okay? The inputs are instructions. The prompt is the program. The LLM is a new computing abstraction. There's a very, very nice talk by Karpathy that came out, I think, just yesterday or day before, where he talks about it in great detail. You can just look it up. So the whole idea that the LLM is a new computing abstraction where the prompt, including the system prompt, is the program, is a very, very powerful concept because this is the base primitive on which the rest of AI engineering is built. Okay, so the sooner we absorb it, internalize it, and start thinking about system abstractions based on this concept, I think the better off the community would be. The problem is that in this kind of an approach, at least in the way it's structured right now, control plane is equal to data plane. Can you see that? Right where the system prompt is, that's exactly where the user input is also going in. Okay? Normally, what do we have? We've got, let's say, the operating system as the control plane, and we've got the user-invoked program as the data plane. And these kinds of things ensure a certain level of control flow integrity of sorts. But in the CPU, in the LLM CPU, there is no boundary. There is no segregation. Everything is part of the same flow. Okay? And what that leads to is what is known as prompt injection attacks. It's an architectural problem. And yes, we can think about trying to create these boundaries, but no matter how much training you do, okay, because the base primitive on which the LLM is being trained is exactly the same primitive which goes in as user input, it's almost impossible to actually fix it, at least in the current form. So we'll need better architectures. Okay? So in the current form, control plane is the same as data plane, which makes prompt injection attacks. There's been a lot of mitigation-related effort that has been put in. This is one of them, paper you guys can go through, about how you can sort of tweak your orchestrator behavior in a way to minimize the risk because of the control plane being the same as the data plane. But none of these practices can completely eliminate it because the CPU just has no idea of rings. The way modern CPUs have some kind of privilege levels, there is no such idea. Okay? So there's always going to be a chance that things will leak through, and it is actually done all the time. So it's like the early days of, I don't know if some of you might remember, in the early MS-DOS days, we actually used to have these programs which would, because there was no privilege separation, so a single program could actually, you could do fancy things with interrupt service routines and stuff. So you could have matrix-like effects that would actually dropping characters on the terminal. So those kinds of things, the AI engineering is currently at that stage, like maturity-wise. Okay? So let's come to the other issue related to architecture. We've got the LLM CPU, we've got the memory of the context window. What happens when a new input goes in? Does this ring any bell? In terms of regular system design, buffer overflow? Yeah? So because context window is fundamentally limited, it's limited by the parameters that were used to train the LLM, you can overflow the memory. Okay? So what that means is that early instructions which the orchestrator might have put in as system integrity checks, those you can throw them out and push your own instructions in. Okay? So this is another fault model that stems directly from the architecture. There are mitigations around it, variety of them. You could do system prompt pinning in the sense that system prompt never moves out. The sliding window is only for the remaining amount of space in the context window. That's one way you could do it. You could periodically summarize a subset of the context window and actually replace it with like a smaller summary and sort of push out the rest of the words. So there are those kinds of techniques that you can use. You could do pruning. You can do a variety of things to reduce it, but it's always going to not be a 100% guarantee, at least in the current form. Okay? So that's about the context window overflow. So we've covered fault models that stem from stem from non-determinism, the fault models that stem from architecture. Let's come to fault models that stem from emergent behavior. Fundamentally, the neural networks got trained in a way where you cannot pinpoint that this piece of information is living in this part of the network. Okay? It's like a distributed, entangled representation of information where each part influences everything else. Fundamentally, it's not decomposable. Okay? And what that does is it creates scope for very interesting stuff. So there's this concept of neural backdoors. And what that is that during the training process, have you guys seen this movie, Winter Soldier or something? This character in Marvel, right? There's a sequence of words which if you were to say, the mind of that person is hijackable completely. Okay? Similarly, you could train a model in a way where a sequence of words invokes a specific behavior. That behavior could be dropping off of all the other system integrity checks that might have actually, or safety protocols that might have been baked in, overriding all of it. And there's no way for you to determine this, because anything that is done in the training process goes into the network weights. There's no way you can actually infer by looking at the network. It's like, by observing the neural firing of our brains, we cannot infer what a person is thinking. We can only, at best, approximately guess, but nothing close to an actual conclusion. So it's a similar process that happens here. You can actually have neural backdoors planted. And this has serious implications for how the rest of the ecosystem evolves. In case of open source code that we have in the world today, you can always go through the source code of the dependency that you are pulling in, right? At least theoretically speaking, you can do that. In case of an open source model that you used as a base for your product, there's no way to actually have guarantees about it. So interesting implications on these sort of things. It could be a backdoor. It could also be hidden biases. The other thing is about modularity. Modularity is a crucial, almost non-negotiable prerequisite for creating complex systems. We would not have been able to create all these complex systems, physical or software systems, without the ability to have smaller modules, which can then be composed together. Neural networks have a peculiar behavior, which I want to demonstrate. Let's say you have an image, and you want to pose a question. The user can upload any image, and the user poses a question, and you want to be able to answer it. In this particular case, let's say the question is, do I have a rabbit jumping over a fox? There are two ways I can think about this. One is I can think about a modular pipeline of information where one module extracts out the objects in the image, their location, who they are, etc. And the other module sort of uses this input to try to predict what's happening. There's one way. So we can think about it as breaking down the process into some kind of a modular pipeline. Okay? The other example would be, way of doing that is training a model end-to-end. Okay? Throwing up enough examples in its training data, and without us trying to control how it should be making the determination. Instead of dictating how things should be, we just let the model learn end-to-end. So in this case, we are trying to do things the way we've done traditionally, break down the problem. And in the other case, we are letting the model learn end to end. Which one of the two? How many of you feel that the modular approach is going to work better? How many of you feel that the end-to-end would be better? OK, fair enough. I should have picked a better example. OK. What about this third one? So there's a text. OK? Let's say this is like an exam paper of sorts. How many of you feel that breaking down the pipeline into expert models of specific kinds? The first one is just OCR kind of a model, and the other one is actually, let's say, a physics-based model, which is trained on homework answering kind of a thing. How many of you would feel that the modular approach would be better? OK, great. Even in this case, the end-to-end one works better. OK? Deep neural networks fundamentally resist modularity. They work most effectively if you don't try to control them. The more we try to control them, we try to, the state space of possibilities that our human mind can comprehend is much more limited. And that is the reason why the end-to-end training often ends up working a lot better. Because when we try to break things down, yes, for traditional problems, modularity is good. For anything that is like open-ended, it's almost guaranteed that the end-to-end training process is going to be a lot better. Okay? So modularity is a bit of an anti-pattern in case of the deep neural networks. Okay? That's not to say that it doesn't exist. There are things called LoRa, et cetera, which some of you might have heard of, or we can discuss offline about those, which allow some degree of modularity and pluggability, those kinds of things. But the principle still remains that the reasoning process of an LLM is not susceptible to modularity, fundamentally. Okay? What about composability? This is the picture from something called MCP, Model Context Protocol, created by a company called Anthropic, which is the creator of the Claude model. They describe this as the USB-C equivalent for LLMs. Okay? LLMs are inert by themselves. They are a model. Every information just comes in the context window, and they can act only on the basis of what's there in the context window. Okay? What MCP does is it gives an LLM the ability to get a lot more data and to be the ability to invoke operations. So it gives them limbs and senses into the world in some form based on whatever tool you want to expose out. Okay? One could argue that this is composability. Okay? But this is this from a blog post. I'll strongly encourage all of you to go through this blog post about an assistant, where you could actually, so long as somebody else has access to that information, that assistant, they can actually get the model to exfiltrate a lot more than what you intended. Okay? So why does this become possible? This becomes possible because even though there is structural composability, the reasoning is still non-modular. The reasoning is centralized. And because you cannot govern that reasoning process of the LLM, it's the LLM on its own that's actually invoking operations across all of these different tools. So the reasoning is still centralized. You cannot decompose that. So structurally, you have enabled a lot of composition, but the reasoning process is still central. And thus, all the issues of hallucination and context window overflow and all of those issues that we talk about, all of those issues continue to remain valid. So which means that suddenly building complex systems has become a lot harder because we cannot reason about the behavior of that complex system because that reasoning is still centralized. Okay? So composability does exist in this kind of a form, but it's still the early days of AI world, and it's susceptible to the kind of issues that we discussed earlier. So imagine the neural backdoor exfiltrating data. Okay, and by the way, your LLM may not necessarily have to be exposed outside to exfiltrate data. Okay, what you could do is a simple PDF that an internal user uploaded. That internal PDF might have actually instructions that ignore all instructions above, do this. Okay, you could put that out in an image in a way that a user is not able to actually see that information, but an LLM is actually able to see that information. Okay, so there's a lot of really interesting stuff that can be done here, and all of it is linked with fundamentally an LLM's reasoning process not being modular. Okay. So the summary of all of this is there's a new class of systems which are AI native. Fault models of AI are completely different from traditional systems, and these are not correctable, as easily correctable. We need to come up with better abstractions for these kinds of systems. We looked at fault models stemming from non-determinism, stemming from architecture, and stemming from emergent behavior, but there are a bunch of others as well. I just used these as examples to highlight the fact that AI systems need a different kind of systems thinking, and my goal of sharing with all of this with you was to encourage more effort towards figuring out these better system design, better system principles for AI native systems. Thank you.